Okay, in this section we're going to look at Kirchhoff's rules. These are rules used to solve complex circuits. These are rules used to solve complex circuits. Using these rules, we can solve circuits that are neither series nor parallel. There are two rules. One of them is called the junction rule. So let's look at the junction rule. Junction rule. This one says the sum of all the currents at a junction is 0. So let's define what we mean by a junction. A junction is a point where two or more wires meet. So a junction is a point where two or more wires meet. Two or more wires meet. Okay, the junction rule says that the sum of all the currents in a junction is 0. Junction rule states that the sum of all the currents in a junction is 0. And a junction is 0. Okay, we can write it as the sum of all the currents in a junction is 0. Okay, now suppose, let's say we have this wires over here. Let's say current I1 comes this way, and then current I2 goes this way, and let's say current I3 goes this way. This rule says the sum of these currents is 0. Okay, this implies I1 plus I2 plus I3 equals 0. Okay, but we have to use the sign convention when we apply these rules. So let's look at the sign conventions. Now, current directed towards a junction like this one is technically positive, while currents leaving the junction are taken to be negative. So the sign convention is currents towards a junction are taken to be negative, are positive, are taken to be positive, and currents going away from a junction, are taken to be negative, Now, in applying this junction rule, it's easier to assume that the variables themselves are positive and then to introduce the negatives outside. Okay, in this formula we're assuming each variable could be positive or negative, but it's easier to assume that the variables are positive and introduce the minus and plus signs outside the variable. So, treating all the variables to be positive, treating the currents I1, I2, and so on are positive, then we can write the junction rule as follows. We can say it's plus or minus I1 plus or minus I2 plus or minus I3 and so on is equal to 0. So When the current is directed towards the junction, we pick the plus sign. When the current is directed away from the junction, we pick the negative sign, and we treat these variables as positive. Okay, so the junction rule could be written as the summation of plus or minus I, okay, equals 0. All right, we're going to treat the variables like positive values, and then if it's negative, we'll just introduce a negative outside. Okay, so if you take the circuit that we looked at before, this one, I1, I2, I3. Now assuming this to be positivist, then this becomes I1 will be positive. We pick the plus sign for I1. Okay, but I2 is leaving, we pick the minus sign. I3 is leaving, we pick the minus sign. So the equation becomes I1 minus I2 minus I3 equals 0, or it becomes I1 equals I2 plus I3. Basically what we're saying is what comes in equals to what comes out. It's a very trivial law. Okay, so in applying this rule, currents towards the junction are taken to be positive. This will be positive. Currents away from the junction are taken to be negative. All right, next we're going to look at the loop rule. That's the second rule, loop rule. But first, let's define what we mean by a simple loop, because we're going to use that later. A simple loop is a non-intersecting loop. Intersecting loop. So this is a simple loop, but this one is not a simple loop. Okay, this is simple, this one non-simple. Okay, so a simple loop is a non-intersecting loop. All right, now let's take the loop rule. Loop rule states that the sum of all the potential differences in a closed loop is 0, and a loop is 0. Okay, so we can write this one as the summation of all the potential differences in a loop is 0. Okay, so you get delta V1 plus delta V2 and so on is equal to 0. So you add up all the potential differences in a loop, in a complete loop, and then the potential differences should add up to 0. Okay, now this could be positives or negatives, so let's look at the sign conventions. That is, when we take them to be positives or negatives, sign conventions. Now, as you know, in a circuit we have two kinds of potential differences: the potential difference of a source and the potential difference of a battery. Okay, so first let's start with a battery. Okay, suppose let's say we have this battery over here. Now, when you add up the potential differences, you can add them in a clockwise direction or in a counterclockwise direction. It doesn't matter which one you pick, but you have to specify them. So if you transverse a battery, remember the negative terminal is positive terminal. If you transverse it from the negative to the positive like this, it's taken to be positive. But if you transverse it from the positive towards the negative, it's taken to be negative. Okay, so this is sign convention for a battery. When you add up the potential difference, if you're going this way, if you're going from the negative to the positive, then the potential difference is taken to be positive. But if you're going from the positive towards the negative, it's taken to be negative. Okay, so the potential difference across a battery is taken to be positive if transversed from the negative to the positive terminal, and negative if transversed from the positive to the negative terminal, from the positive to the negative terminal. Okay, this is a sign convention for a battery. If when you add up the voltage, you're crossing the battery from the negative towards the positive, you take it to be positive. But if you're transversing it from the positive towards the negative, you take it to be negative. So these are the sign conventions of a battery. Now let's look at the sign conventions of a resistor. Okay, now let's say we have this resistor. Now whether it's positive or negative depends on the direction of the current. Let's say the current is flowing in this direction. Now if this is transversed in the direction of the current, like this, you see, as the charges cross the resistor, they lose energy. So it's going to be taken to be negative. If it's transversed in the direction of the current, is taken to be positive. Okay, but if it's transversing in the opposite direction, in the direction of increasing potential difference, then it's taken to be positive. Okay, so for a resistor, if it's transversed in the direction of the current, it's taken to be negative, and if transversed opposite to the direction of the current, is taken to be negative. Okay, so the sign convention is the potential difference across a resistor is taken to be negative if transversed in the direction of the current, and positive if transversed opposite to the direction of the current, opposite to the direction of the current. Okay, now we're going to look at some examples. Let's look at the following simple example. Let's say we have this circuit. It has a battery like this. Maybe let's say it's 6 volts, and then we have a resistor over here. Maybe it is let's say 5 ohms, and then we have another battery over here. Let's say it's 2 volts, and then maybe another resistance over here. Let's say it's 10 ohms. Okay, now to start with, we don't know which way the current is going. Okay, well, in this case we can guess because this one is pushing by 6 volts, this one is pushing, but anyway, most of the time we're not going to know which way the current is going. So you don't have to know which way the current is going. You can assume any direction, clockwise or counterclockwise. The answer will tell you whether it's positive or negative. If the answer turns out to be positive, then the assumed direction is correct. But if the answer turns out to be negative, the assumed direction is opposite to the actual direction. So the answer of the current will tell you the direction of the current. So you just assume any direction. If your answer is positive, you're assuming direction is the correct direction. If your answer is negative, the actual direction is opposite to the assumed direction. Okay, so let's assume the current is flowing, in this case, let's say in this direction. Okay, that is in a counterclockwise direction, and let's call it I. Okay, so of course the question is to calculate the current in the circuit. Calculate the current in the circuit. All right, so we're gonna apply the loop rule. Okay, the loop rule. Let's apply the loop rule. Now, it doesn't matter which way you go when you apply the loop rule, but you have to decide. You can go in counterclockwise direction or you can go in a clockwise direction. It doesn't matter which way you go. Okay, suppose let's say we decide to go this way. Okay, the loop rule says if you add up all these potential differences in a closed circuit, you should get 0. Okay, and then you have, of course, you have to decide where you want to start. Let's start over here, and let's go in a counterclockwise direction like this one. Okay, let's start over here. So the first thing we encounter is the battery. You see, we're transversing the battery from the negative to the positive. So according to our sign convention, this one is taken to be positive. Okay, so the first term is, this is our formula, the sum for delta V is equal to 0. So the first term is plus 2 volts. Okay, for this battery over here, and then we encounter this resistor over here. Okay, now according to our assumption, the current is going this way, so we're transversing this resistor in the direction of the current, so it's going to take to be negative. Okay, and according to Ohm's law, the potential difference is resistance times current. Okay, so it's going to be negative, and it is current times resistance. Okay, we keep going, and then we encounter this battery over here. But now when you go this way, you see we're transversing it from the positive to the negative. Okay, so this one is taken to be negative according to our sign convention. We're going in the direction of decreasing potential. Okay, so that's going to be negative 6 minus 6. We keep going, we get this resistor, we're still going in the direction of the current. Okay, so when you transverse a resistor in the direction of the current, it's taken to be negative. All right, and the potential difference is resistance times current, so you've got minus 5i, minus 5i. Now you see we're back at where we started, and so we should add up all this potential difference to 0. Okay, so this should be equal to 0. So what do you have? We add this together, we've got minus 15i. Okay, and this one is negative 4, the other side becomes 4. So the current is negative 4 over 15 amps. Okay, now this negative sign is very important, because when we started solving the problem, we assumed that the current was going in a counterclockwise direction, but since our answer turns out to be negative, it follows the direction of the current actually clockwise. The negative sign implies that the actual direction is opposite to the assumed direction. Opposite to the assumed direction. So the assumed direction was counterclockwise, therefore direction of current is clockwise. Direction is clockwise. Okay, because we assume it to be counterclockwise, but the answer turns out to be negative, therefore the actual direction is clockwise. So the current actually is flowing in this direction, all right? Okay. Now we're going to solve a circuit involving 2 loops, okay? Complex circuit. Another example. Okay, so suppose we have the following circuit. Maybe we have this battery over here, which is longer. We have a resistor over here. Let's say this is 6 volts. Let's say this is 2 ohms. And then we have another resistor over here. Let's say it's 4 ohms. And then we have this potential difference over here. Let's say it's 8 volts. Okay. And then let's say we have this resistor over here. Let's say it's maybe 5 ohms. Okay. And then maybe we have this potential difference over here. We have this circuit. All right. So when you apply, well, first let's apply the junction rule. Okay, well, the question is solve for the currents, for all the currents in the circuit. Solve for all the currents in the circuit. Okay, so we're going to say the rules that we need to follow to solve these problems. The first step is assign a variable and direction to all the currents in the circuit. So remember, the number of different currents is equal to the number of wires. So in this case, how many wires do you have? We have one wire over here, you've got a second wire, you've got a third wire, so we're going to have 3 currents. All right, so we don't have to know the direction of the current before we start. We just assign any direction and the answer will tell us whether our assumption is right or wrong. Okay, so we don't have to worry about the direction to start with. We can assume any direction. Okay, so let's do that. So we have 3 currents in this case. We have current in this wire, we have current in this wire, we have current in this wire. Okay, let's call the current in this wire I1. Let's assume this direction, and then let's call the current in this wire I2. Let's call the current in this wire I3. Okay, so we have assigned variables and we have assumed directions. We don't know what the directions are, but these are just assumptions. And then the final answer will tell us whether our assumed direction was right or our assumed direction was wrong. Okay, all right. And then the second process is, if there are n junctions, apply the junction rule to n minus 1 of them. The reason is the n's junction doesn't give you an independent equation. Okay, if you apply, for example, in this case we have 2 junctions. If you apply the junction to both of them, basically get 2 identical equations. So if there are n junctions, you have to apply them to n minus 1 of the junctions. All right, so we have 2 junctions over here, so we're going to apply to only to one of them. Let's apply to this one. Okay, so we're going to use the junction rule. This one, I mean the sign conventions for the junction rule. I1 is going towards the junction, so we're going to take it positive. Okay, we're going to take the plus sign. And I2 is going away from the junction. This is over here, so we're going to pick the minus sign. Minus I2 is the positive sign. And I3 is leaving the junction, so we're going to pick the minus sign. So the sum of all the currents in the junction should be 0. So we have the following. Okay, so what we can do is we can eliminate one of the variables right from this equation. We have 3 variables. If you carry all the variables, you can get 3 equations in 3 variables, and that is not easy to solve. So what we can do is we can eliminate one of the equations right from here. Okay, so we've got I1 equals I2 plus I3, right? Now let's eliminate I3. We have I3 equals I1 minus I2, okay? So instead of I3, we're going to use I1 minus I2, okay? That will leave us only with two variables, okay? From now on, I'm going to use I1 minus I2 for I3. If I do that, I'm going to have only two variables, and then I will need only two equations to solve the problem, okay? So we're done with the junction rule, all right? Now, the third rule is apply the loop rule to all of the simple loops. Remember, not to all loops, but to all of the simple loops, okay? So in this case, how many loops do we have? We have three loops. This is one loop, this is another loop, but we have also another loop over here. But this loop is not a simple loop, okay? It's intersecting loop. So we have only two simple loops, this loop and this loop, okay? Let's call them loop A and loop B, okay? So we have only two loops, all right? So if there are two loops, two simple loops, we're going to apply the loop rule to these two simple loops, not to this non-simple loop. You apply the loop rule only to the simple loops, okay? All right, and then to do that, first assign transversing directions to each loop. Assign transversing directions to the simple loops. So the direction could be clockwise or counterclockwise, it doesn't matter, but you have to specify them because the sign conventions depend on the transversing direction, okay? So let's say we decide to go this way for A and maybe in the opposite direction for this one, and then we go this way for this one, okay? So we're going to add up the potential differences in a counterclockwise direction for this one, but we're going to add them in a clockwise direction for this one. And then of course you have to decide where you want to start. Let's say this is starting point for loop A, and let's say this one is the starting point for loop B, okay? So we're going to apply the loop rule to loops A and B, okay? Let's do that. We're going to start with loop A, okay? So we're going to start, this is our starting point, it doesn't matter where we start, and we're going in a counterclockwise direction, okay? And this wire, the current is I1. You see this wire? This is one wire. So the current is I1 over here. Now, the current is going this way, you see? But we're crossing it opposite to the direction of the current. So the potential difference across this resistor is going to be positive, okay? And so that is resistance 2 times the current I1, and it's going to be positive because it's being transversed opposite to the direction of the current. The current is going this way, but we're transversing it this way, okay? So the first term is going to be 2I1, okay? Now we keep going, we get this, we're going this way, we get this, this battery. We're transversing it from the positive to the negative. So according to our sign convention, it's going to be taken to be negative, all right? So you've got minus 8. All right, we keep going. We have this resistor over here. Now look, the current is going this way, but I'm transversing it opposite to the direction of the current. So the potential difference across this resistor is going to be taken to be positive, okay? So 4 times the current, I2, is going to be positive, okay? So you've got plus 4I2, all right? I keep going, I find this battery. I'm crossing this battery from the positive to the negative, so the potential difference is going to be taken to be negative according to our sign convention, because I'm crossing it from positive to the negative. So that's minus 6. So you've got minus 6. I keep going, I'm back at where I started, and then I add all of them up to 0. Okay, so this is my first equation. Simplify it. So you've got 2i1 plus 4i2. You take the other side, 14. Okay, and then we can divide the whole equation by 2. You've got i1 plus 2i2 equals 7. Okay, so this is the equation obtained from loop 1. Let's call it equation 1. Okay, but you know we have two variables, so we need another equation to solve this. We need another equation to solve this one. So that other equation is going to be obtained from loop B. We're going to do the same thing for loop B. Okay, so for loop B, we have decided to go in a clockwise direction, and we decided to start here. Okay, well, let me give this potential difference. This battery, let's say it's 2 volts. Okay, so I'm going this way now. You see, this is a positive terminal. I'm going to the positive and negative, so that is going to be taken to be negative. So that's minus 2. All right, I keep going. I encounter this battery. I'm crossing this battery from positive to negative, so it's going to be taken to be negative. Okay, that's minus 8. Minus 8. I keep going. I encounter this resistor over here. But remember, the current's going this way, I'm going this way. So the potential difference across the resistor, according to our sign convention, is going to be positive. So that's 4i2. Okay, so the next potential difference is 4i2. Okay, let me keep going. I keep going. I encounter this resistor over here. Okay, now you see the current is going this way, which is i1 minus i2, and the transversing direction also going this way. So I'm transversing the resistor in the direction of the current, and so it's going to be taken to be negative. So this one is minus 5 i1 minus i2. Okay, and now I'm back at where I started, and I add up all the potential difference to 0. So that's my equation. All right, so let's simplify this equation. We've got minus 10 over here, minus 10 plus 4i2 minus 5i1 plus 5i2 equals 0. Okay, so we have minus 5i1 over here, and then we have 4 plus 5, 9i2, and then we take the number the other side. We have 10 on the other side. Okay, so this is our second equation. Okay, let's call equation 2. Now there are two ways of solving equations like this. They're the method of substitution and method of elimination. So you can use which one you feel comfortable with. But probably in this case, you know, it might be easier to use substitution because it's easy to express I1 in terms of I2. Okay, so from equation 1 we have the following. Equation 1 implies, okay, I1 equals 7 minus 2I2. Okay, I1 equals 7 minus 2I2. In either case, our goal is to get an equation in a single variable. Okay, so if I express I1 in terms of I2, I'll be able to solve the problem. Okay, so let me write the second equation again. It is negative 5I1 plus 9I2 plus 9I2 equals 10. Okay, equals 10. Now we're going to replace I1 by this one. Okay, our goal is to get an equation in a single variable. If you do that, then we'll have an equation item, then we can solve it. Okay, so negative 5, this one over here, 7 minus 2I2 plus 9I2 equals 10. Okay, so you see we have an equation in one variable, and so we can solve it. All right, so let's simplify. We get negative 35 plus 10I2 plus 9i2 equals 10. Okay, so you've got 19i2, and then 35 plus 10 is 45. So the value for i2 is 45 over 19 amps. Okay, so the answer for i2 turned out to be positive. What does this mean? The assumed direction for i2 is actually correct. So i2 is actually flowing in this direction. Okay, now let's calculate i1. We can use this formula to calculate i1. Okay, so you've got i1 equals 7 minus 2i2. Okay, and we already know what i2 is, so that is 7 minus 2, 45 over 19. Okay, so let's add up this. So 7 times 19, 70 plus 63 is 133, and this 33 minus 90 over 19. Okay, and that is 43 over 19 amps. Okay, so I1 also turned out to be positive, so our assumed direction is correct. Okay, all right, now remember I3 is I1 minus I2. Remember from junction rule we obtained I3 equals I1 minus I2, so you calculate I3 too, and I3 is I1 minus I2. Okay, so I1 we just obtained 43 over 19. This is 43 over 19, and I2 is 45 over 19. 45 over 19. Okay, so that gives me negative 2 over 19. Okay, amps. So what does the negative mean? The direction of I3 is opposite to the assumed direction. Okay, so we assumed I3 was going this way, but actually I3 is going in the opposite direction.